Now let's take the previous example where I have selected the contour in the S-plane in such a way that the selected contour encircles only one pole. So for this condition, the number of zeros encircled by the contour in the S-plane, which is Z, is equal to 0, and number of poles encircled by this contour P is equal to 1. So Z minus P is going to be minus 1. That is, Z minus P equal to minus 1 indicate that the corresponding plot in the f of S plane will be encircling the point 0 or encircling origin 1 times in anti-clockwise direction. So, if the selected region in the S-plane has equal number of poles and zeros, that is, I am mentioning about Z is equal to P, then Z minus P is going to be 0. So, f of S contour will not encircle origin. So, if the selected region in the S-plane is having equal number of poles and zeros, then the f of S contour will not encircle origin. If the selected region has more number of poles than zeros, then the net encirclement will be in anti-clockwise direction. And if the selected region in the S-plane is having more number of zeros, then the net encirclement will be in clockwise direction, as Z minus P is going to be positive. So, getting into Nyquist stability criterion, let's assume an open loop transfer function as we have discussed earlier. G of S H of S is equal to S minus Z1 into S minus Z2 up to S minus Zm, the whole divided by S minus P1 into S minus P2 up to S minus Pn. The characteristic equation of this system can be written as 1 plus G of S H of S, which will be turned around as S minus P1 into S minus P2 into S minus Pn plus S minus Z1 into S minus Z2 up to S minus Zm, whole divided by S minus P1 into S minus P2 into S minus P. So, comparing the open loop transfer function G of S H of S and the characteristic equation 1 plus G of S H of S, I can make this conclusion that both these functions are having the same poles, because 1 plus G of S H of S and 1 plus G of S H of S and G of S H of S are having the same denominator. That means that they are having the same poles. Also, the characteristic equation 1 plus G of S H of S, I have S minus P1 into S minus P2 up to S minus Pn plus S minus Z1 into S minus Z2 up to S minus Zm divided by S minus P1 into S minus P2 up to S minus Pn, which is equal to 0. And the closed loop transfer function, which is given by G of S by 1 plus G of S H of S, that is G of S divided by this function, will turn around as G of S into S minus P1 into S minus P2 into S minus Pn divided by this function S minus P1 into S minus P2 up to S minus Pn plus S minus Z1 into S minus Z2 into S minus Zm. And if I compare the characteristic equation 1 plus G of S H of S and the closed loop transfer function G of S divided by 1 plus G of S H of S, I can make the conclusion that both these functions, like the numerator of the characteristic equation is same as the denominator of the closed loop transfer function. That means that zeros of the characteristic equation is same as the poles of the closed loop transfer function. So I have a conclusion over here. Poles of the closed loop system are the zeros of the characteristic equation. That is very important conclusion for Nyquist stability criterion. That is, poles of the closed loop transfer function will be same as the zeros of the characteristic equation. Why it is important is that For examining the stability of a closed loop transfer function, I need to look into the location of the poles. If the poles of the closed loop transfer function are on the right half of S-plane, then the system is going to be unstable. So, instead of going for the location of closed loop poles, I will be looking for the location of the zeros of the characteristic equation. So, to check the stability of closed loop system, I will be checking the location of zeros of the characteristic equation. That is very important. So now I will state the condition for stability. For a closed loop system to be stable, 1 plus g of s h of s should not have any zero on the right half of S-plane. That means that if 1 plus g of s h of s is having a zero on the right half of S-plane, that means that closed loop system is having a zero on the closed loop system is having a pole on the right half of S-plane. So let's apply principle of arguments over here. I'm taking an S-plane. My aim is to check for zeros of 1 plus g of s h of s in the right half of S-plane. So I am taking a contour in the S-plane in such a way that this contour encloses entire right half S-plane, so that the radius of this semicircle I have chosen will be infinity. So I have chosen a contour which covers the entire right half S-plane. So first I need to locate the poles of 1 plus g of s h, which is very easy because poles of 1 plus g of s h of s is same as the poles of g of s h of s, which we have seen. So I can locate the poles of g of s h of s or 1 plus g of s h of s in the S-plane. But I don't know the location of zeros of 1 plus g of s h of s, which I need to investigate. So my aim is to find the location of or check whether the function 1 plus g of s h of s is having any zero on the right half of S-plane, which will indicate the instability of the system. So it is easy to locate the poles of 1 plus g of s h of s as they are same as the poles of open loop transfer function g of s h of s. I don't know about the zeros of 1 plus g of s h of s, which I want to check. Now I have clear idea about the location of poles of 1 plus g of s h of s because poles of 1 plus g of s h of s are same as the poles of g of s h of s, but I don't know about zeros. Let the number of poles on the right half of S-plane be p. That means that if 1 plus g of s h of s is having p number of poles on the right half of S-plane, and if the right half of S-plane does not contain any zero, so I am stating once again, I have taken a contour which covers the entire right half S-plane, and I am assuming that the right half of S-plane has p number of poles of the open loop transfer function g of s h of s. And let's assume that the right half of S-plane does not contain any zeros. So I have in the right half of S-plane p number of poles in the right half of S-plane and no zeros. And I plot the mapping. The number of encirclements made by f of s contour against origin should be what? Should be 0 minus p, z minus p. That means that minus p. So if the right half S-plane does not contain any zero, the f of s contour should encircle origin p number of times in anti-clockwise direction. I will state once again. If the S-plane f of S-plane has p number of poles in the right half and does not contain any zero in the right half, then the number of encirclements made by f of s contour n will be 0 minus p, which is minus p. That means that the f of s contour should encircle origin p number of times in anti-clockwise direction. So no zeros on 1 plus g of s on the right half of S-plane means that stable closed loop system. So for stability, n should be equal to minus p. It can be stated like this, that is, for a system to be stable, the 1 plus g of s h of s contour in the 1 plus g of s h of s plane should encircle origin as many times as the number of right half S-plane poles in anti-clockwise direction. We'll simplify like that. If the system is having, or open loop system is having p poles on the right half of S-plane, so for the system to be stable, n should be number of encirclement made by the f of s contour against origin should be minus p. If I have two poles on the right half of S-plane, then the number of encirclement made by the f of s contour should be minus 2, that is 2 encirclements in anti-clockwise direction, so that z will remain 0. Z is equal to n plus p. Sorry, z is equal to n plus p. In practice, instead of plotting 1 plus g of s h of s contour and checking the encirclement against origin, I will be plotting only g of s h of s, and the encirclement around the point minus 1 will be checked. So instead of going for a plot of the characteristic equation 1 plus g of s h of s, I will be plotting g of s h of s, and instead of checking encirclement against origin, I will be checking the encirclement against the point minus 1 plus j0. So the Nyquist stability criterion can be stated like this. If the g of s h of s contour in the g of s h of s plane encircle the point minus 1 plus j0 in anti-clockwise direction as many times as the right half S-plane poles, then the closed loop system is stable. I will repeat once again. If g of s h of s contour in the g of s h of s plane encircle the point minus 1 plus j0 in anti-clockwise direction as many times as the right half S-plane poles, then the closed loop system is stable. Thank you.